Hello everyone, myself Anisha. Today I am going to prepare a audio recording for visual impaired students on the topic Bioinorganic Chemistry from Pradeep's Inorganic Chemistry Volume 3rd by Dr. K. Bhasin. Let's start. Inorganic Chemistry. Inorganic chemistry deals primarily with salts and complex metal ions, whereas bioinorganic chemistry deals majorly with inorganic chemistry when applied to biological systems. Thus, bioinorganic chemistry can be regarded as the branch of science that deals inorganic chemistry with life progress by recognizing the role of metal ion in the normal growth and function of biological process. In brief, bioinorganic chemistry highlights role of metal ion in biology. Bioinorganic chemistry is a rapidly developing area of chemistry because of its importance in biological system. The essential bioinorganic role of fused elements have been known for many years. This chapter will focus on the important role of metal, non-metal, and their component in biological system. Progress, essential and trace elements. We think that the chemistry of life is solely composed of organic molecules. It is wrong concept. In fact, there is a long list of inorganic compounds that are essential to living system. For example, the skeleton and integumental material in higher animals is composed majorly of inorganic materials, and the lifetime composition of oxygen by a living entity is a major fraction of the material need. In addition, water, oxygen, calcium phosphate, and calcium carbonate are the major inorganic constituents of living material. In terms of quantity, table 5.1 lists the abundance element in earth crust and in oceans compared with some abundance in typical mammals. This is the list of all known elements. It is about 30 elements that have been recognized as essential and indispensable to life. Out of 30 elements, 15 of them are metals. The essential elements are needed for the growth and normal function of the element and plant. Absence of these elements results in several malfunctioning of living organisms. Thus, an element may be considered essential when it is insufficient intake produces an impairment of normal functions, and in restoration release the impaired functions. Some of these elements are required in bulk of macroscopic amount to all forms of life and classified as bulk elements. Some of the bulk elements are required for structural purpose, skin, bones, egg cells, various organs, while these rest are used as minerals. In other words, the absence of essential element, the organism can neither grow nor complete its full life cycle. The essential elements can be further subdivided into two groups: bulky elements and trace elements. Bulky elements, essential elements that are formed in higher concentrations. Trace elements, essential elements that are present in low concentration. Bulky quantities of group 1 and group 2 elements are required mainly to balance the electrical charge associated with the negatively charged macromolecules in the cell, and also to maintain the osmotic pressure inside the cell. The reaction flask of a living organism in the cell. In addition, the transition elements and the heavier elements of the P group may play an important role in the bioinorganic chemistry. Some of the inorganic elements are required in small quantities and are classified as trace or ultra trace elements. These are different types of essential elements present in the living system are classified in the table 5.2. Bulky structural elements: hydrogen, carbon, nitrogen, oxygen, phosphorus, sulfur. Mineral elements: sodium, potassium, magnesium, calcium. calcium, chlorine, iron, copper, zinc, vanadium, nickel, cadmium, lithium, lead, tin. These are trace elements. Ultra trace elements metals are manganese, molybdenum, chromium, silicon, arsenic, and selenium. Non-metals: fluorine, iodine, boron. It is important to note that all the elements displayed in table 5.2 are required by all plants and animals. For example, sodium iron Na positive is a special importance to the higher animals. However, it is not essential to many bacteria and plants. The ultra trace elements by boron, aluminum, vanadium are needed by some higher plants. Molybdenum is essential to only those organisms which derive their nitrogen from inorganic sources. Selenium is an essential micronutrient to mammalian species, but proves to be a toxic at higher levels. Selenium deficiency in human results in a degenerative condition of heart tissues known as Cushing disease, in which it was It was endemic because of extremely low selenium level in the oil, coupled with a population that entirely depends upon local grown grains. It is important to know that even some essential elements may prove to be toxic if consumed in a large quantities. Essential bulky elements: sodium and potassium. We have learned that both sodium and potassium are essential for life processes. For example, we need at least 1 gram of sodium ion per day in our diet. However, because of our habits to adding salts on food, some people consume as many as 5 times more than required. However, intake of potassium is not a problem. Instead, potassium deficiency is more common. We must include potassium-rich foods such as bananas and coffees in our diet. In organic chemistry, we always think of similarities between sodium and potassium. However, in biology, it is the difference between sodium and potassium which plays important role. Cell pump out sodium ions of cytoplasm, where the cell pump the potassium ion inside. This ion transport is sometimes called the sodium pump and involves both the active expulsion of sodium ion and the active take up of potassium ion. It is the difference in total alkali metals ion concentration inside and outside cell that produces an electrical potential across the cell membrane, which is important for the functioning of nerve and muscle cells. The transport of ions requires energy, and this is obtained by the hydrolysis of ATP, adenosine triphosphate. It is estimated that hydrolysis of one ATP molecule to ADP, adenosine diphosphate, provide enough energy to make 3 sodium ions out of the cell and 2 potassium and 1 hydrogen ion back into the cell. Calcium and magnesium. Both calcium and magnesium are present in body fluid. Magnesium 2 positive ion are concentrated in the animal cell, and the calcium 2 positive ion are concentrated outside the cell. This is similar to the presence of potassium ion inside the cell, whereas sodium ion outside the cell. Calcium ions are present in the external skeleton of creatures such as shellfish and corals. The material used in the calcium carbonates. Creatures with interior skeletons such as mammals and reptiles use calcium hydroxide phosphate CA5OH whole thrice the and the enamel on the teeth of fluoropeptide 3. Both these compounds are highly insoluble. Important minerals used in the biological minerals are in table 5.4. Calcium 2 positive ions are important in blood clotting and are required to trigger the contraction of muscles such as those that control of beating of the heart. In fact, some types of muscle cramps can be prevented by increasing of the intake of calcium ions. Table 5.4. Calcium containing minerals in biological materials. Minerals formula, organism and locations. These are a decrease in calcium positive content of blood either due to dietary deficiency or the form of an insufficiency of the parathyroid hormone may lead to disease called a tetany. On the other hand, an increase in concentration of calcium ions in the blood may lead to recalcification of several internal organisms. The absorption of dietary calcium ion from the interstitial tract may be prevented by the simultaneously ingestion of organic acids such as example oxalic acid with which it combines to form an insoluble salt. It means that the availability of dietary calcium ion is greatly affected by the other content of the constituent of the diet. Both calcium and magnesium ions are excreted mainly by large intestine instead of the kidney. Magnesium, because of its high charge radius ratio and the consequent strong hydration such as manganese, aqua manganese. Play important biological role that are different from those of the calcium. It acts as a counter ion to the negatively charged group in the nucleotide and polynucleotide. One of the most important nucleotide is ATP, which serves as the fundamental energy source of the living cells. ATP is thus known as energy-rich molecule and is used to derive most of the chemical reactions of the cell. Manganese ion form a complex with ATP. It has been observed that all transphosphorylation reactions involve ATP process smoothly in the presence of manganese ion. ATP is an anhydride of phosphoric acid. The hydrolysis of anhydride is a very favorable reaction. Thus the hydrolysis of ATP to ADP shows in the reaction below liberates 30.7 kJ per mole of the energy at pH 7. The living system thus utilize the energy to drive energy requirement biological process. This is the structure of ADP and ATP. It has been observed experimentally that the activating effect of magnesium ion transphosphorylation may be duplicated in vitro by manganese, calcium, cobalt, zinc, and nickel ions. The most important aspect of biochemistry of manganese is its role in photosynthesis. Magnesium containing chlorophyll using energy from sun and convert into carbon dioxide and water into sugar and oxygen. This is the reaction. Without the oxygen from the chlorophyll reaction, this planet would still be surrounded by a dense layer of carbon dioxide. In addition, without the sugar energy source, it would have been difficult of life to progress from plants to animals. It is important to note that magnesium ion site in the middle of chlorophyll molecules and hold the molecule in a specific configuration. Magnesium has only one possible oxidation number, that is +2. As a result, the electron transfer reaction involved in photosynthesis can progress without interference from the metal ion. Phosphate. Phosphorus is an important animal element for the life progress. For example, free hydrogen phosphate and the dihydrogen phosphate ions are involved in the blood buffering systems. Phosphate is the linking unit in the sugar esters of DNA and RNA. Phosphate unit make up of part of ATP, the essential energy storage unit in the living organisms. Bone is a phosphate mineral. The commonly called minerals apatite is calcium hydroxide phosphate. The presence of phosphorus in bones and its function is regulation of pH of blood constituent important feature of phosphate. It is important to mention that the normal formation of bones depend upon the relative amount of dietary phosphorus and calcium. In addition to Essential trace elements. Among the known trace elements, the three most prominent biological active metals are iron, copper, and zinc. The remaining trace elements, excepting boron fluoride, are used in very small amount, less than 10 mg in adult human being, and are referred as ultra trace elements. The trace elements are known to play important role as metallurgy enzymes. The iron is essential in small amount for both plants and animals' life. However, like copper and selenium, it is toxic when used in large quantities. Biological iron is most important transition element and is found in greatest abundance in biological system in the form of porphyrin complex as or heme such as hemoglobins and myoglobins. Porphyrins as macrocyclic ligands and are derivatives of porphyrin. A human weight a human body weight is about 70 gram, contain about 4.3 gram of iron. Nearly 70% of this iron is present in hemoglobin and about 30% in myoglobin. The remaining 23 of body iron is present in the ferritin. Ferritin is present in spleen, liver, and bone marrow. It consists of a shell of linked amino acids called apoferritin surrounding a core of an iron oxohydroxophosphate. The core is a cluster of iron ions, oxide ions, and hydroxide ions and phosphate ions with the composition of FeO4 whole 8 FeOPO3H2. It is very large, containing up to 4500 iron ions with its hydrophilic coating. This large aggregate is water soluble and is concentrated in the spleen, liver, and bone marrow. Apoferritin protein can be prepared by ferritin by reduction of ferric ions to ferrous ions at pH 4.5, followed by the removal of Fe2 positive by dialysis. The formula weight of The formula weight of apoferritin is nearly 46500. Ferritin can be synthesized in the laboratory with properties similar to natural ferritin. It can be prepared by treating crystalline apoferritin with an inorganic iron salt in the presence of oxygen. Ferritin is probably formed in vivo by an analogous process. Various steps involved in the pathway of Fe2 positive ion from the foodstuff to hemoglobin and to ferritin involve the following processes. Fe2 positive of the bound dietary material is reduced to Fe2 positive in the gastrointestinal tract. After absorption into the cell of intestinal mucosa, Fe2 positive is incorporated into ferritin as Fe3 positive ion. The Fe2 positive ion in mucosa is also converted to Fe3 positive plasma bounded by iron binding globulin named transferrin. Plasma Fe3 positive in equilibrium with iron in the liver, spleen, bone marrow, etc. The following changes that occur in are summarized in the scheme 5.1. This is the pathway of iron third from the foodstuff to hemoglobin and to ferritin. Zinc. Among the trace essential elements, zinc is the second iron, only to iron in importance. Zinc is essential to all organisms and play an important biological role in the enzyme system of animals and plants. Humans contain about 2 grams of zinc and is one of the most important and critical element in our diet. Deficiency of zinc are not life-threatening but contribute to fatigue, lethargy, and related symptoms. Zinc 2 positive iron ion is a soft acceptor compared to other divalent ions by Mg2 positive, calcium 2 positive, Mn2 positive, and act as the stronger Lewis acid towards many biomolecules. Compared to zinc and copper, ions is also soft but has an additional intermediate oxidation state, that is copper ion. Different oxidation states of copper may allow different redox reactions and complicated its behavior. The complex of zinc ion are much more labile than the corresponding complex of Mg positive, nickel positive, manganese positive. This faculty is the role of zinc ion in enzymes, since zinc positive 2 positive ion is completely resistant to redox change at biological potential. Its role cannot be affected by changing the redox potential in the organisms. A number of enzymes containing zinc ion are known. The most important of all the enzymes is the carbonic anhydrase. It is present in the red blood cell and involved in the respiration. It speeds up the absorption of carbon dioxide by red blood cell in muscles and other tissues. On the other hand, in reverse reaction, it involves the release of CO2 in the lungs, and reaction is pH independent. CO2 plus H2O carbonic anhydrase एंजाइम की प्रेजेंस में H2CO3 एक्वस प्रोडक्ट मिलता है. Thus the zinc containing enzyme carbonic anhydrase catalyze the otherwise low carbonic acid carbon dioxide equilibrium reaction. The carbonic anhydrase has a common for coordinated environment around zinc 2 positive ion, in which 3 of the ligands are immutable nitrogens of 3 histidine, and the fourth is water molecule on hydroxy ion as shown below. A water molecule coordination to a zinc ion has peaked near 7, and thus the role of zinc is to reduce the basicity of hydroxy ions, such as a high efficiency concentration of hydroxy ions exists in the approximately neutral medium. Another important enzyme containing zinc 2 positive ion is carboxypeptidase. It is present in the pancreatic juice and is primarily involved in the digestion of proteins by animals and protein metabolism in plant and animals. This enzyme catalyzes the hydrolysis of terminal peptide link in the carboxyl end of the peptide chain. The enzyme is selective and the work only when R group is in the terminal amino acid in aromatic and branch aliphatic chain and has the L configuration. Next is copper. Copper is third most biological important transition metals after iron and zinc. Human beings need around 8 mg of copper daily. A deficiency of copper than the optimum value results in the inability of animals to use iron stored in the liver. As a result, the animals suffer from anemia. The copper is bound to protein in the body either as metalloproteins or as enzymes. Excess of protein is highly poisonous, particularly to fish. This is the reason it was always advised not to throw copper coins in the fish pool for good luck. Human beings can excrete any excess of copper, but a biochemical defect can result in copper accumulation in the liver, kidney, and brain. The illness caused by the excess of copper is called Wilson's disease. It is a hereditary storage of Plasmic causing copper accumulation in the liver, kidney, and brain. Patients suffering from Wilson's disease are cured by the administering ethylene diaminotetratic acetic acid (EDTA), which forms soluble copper complex. Thus, soluble copper complex can be excreted harmlessly through urine. At the same time, many other essential metals involved in other enzymatic reactions from EDTA complex or excreted. Thus, the EDTA treatment can upset many unwanted enzyme reactions. As a result, almost utmost care should be taken in monitoring Williamson diseases. Hemocyanin is a copper-containing protein which is important as an oxygen carrier in some invertebrate animals. Despite its name, it is non-hemoglobin protein. It is found in the blood of snails, crabs, lobsters, octopus, and scorpions. The oxygenated hemocyanins are blue-colored, unlike human blood, and have one dioxygen molecule attached to the two copper. Deoxygenated hemocyanin contain copper 1 and is also blue. Selenium. Selenium is an essential to health. All classes of organisms metabolize selenium in human and other mammals. Cirrhosis disease arises from either excessive or insufficient dietary selenium. The toxic effects of selenium have long been unknown, particularly from grazing animals. In soils with high selenium content, some plants accumulate large amount of selenium as methylcyanate in order to keep selenium away from their metabolic machineries. Animals that graze the selenium accumulating plants develop several toxic reactions, including blind, sterile, and alkali disease. Selenium poisoning in humans is rare, but it has occurred where mines can cause selenium to be leached from the soil into drinking water supplies. Loss of hair and nails is seen in cases of human selenium toxicity followed by anemia and jaundice. Although selenium is a toxic at a high level, selenium is an essential micronutrient for mammalian species. Selenium deficiency in human results in a degenerative conditions of the heart tissue known as Cushing's disease. This disease is named by country in China. The accepted minimum daily requirement of selenium for adult human is 70 microgram. Many types of food provide selenium, particularly seafood, meats, grains, and onion family. Mammals and birds require selenium from productivity of the enzyme glutamine peroxidase, hydroxyperoxidase, and organic peroxides, which cause oxidative damage to cellular components and enzymatically destroyed by the selenoprotein. Such antioxidant activities such as the glutamine peroxide and therefore selenium protect against oxidation-induced cancer. Next is chromium and molybdenum. Trace amount of chromium and molybdenum are necessary in the diet of mammals. Chromium and insulin are both involved in maintaining the correct level of glucose in the blood. A deficiency of chromium or an inability to use the chromium 3 positive ion result is the removal of glucose from the blood as fast as normally and leads to the diabetes. Compounds containing chromium, example dichromate or chromate, when ingested or absorbed through skin are carcinogens. Therefore, almost case must be taken while using K2CR2O7 or K2CRO4. Essentially, while performing titration, molybdenum is the most biological important member of chromium family. It has heaviest element to have a wide range of functioning in living organisms. The most important molybdenum enzyme is nitrogenase. Thus, the nitrogenase containing two proteins, that is the molybdoferoxin and azoferoxogen. Molybdoferoxidin is air sensitive and brown colored species containing two molybdenum enzyme 24 to 36 iron atoms, 24 to 36 sulfur atoms together with a protein. It has a molecular weight of about 225,000. Azoferoxidin is yellow, air sensitive, and a derivative of ferroxidin Fe4S4. It has a molecular weight in the range of 50,000 to 70,000. The enzyme nitrogenase occur in bacteria and reduce the inert dinitrogenase of the atmosphere to ammonium chloride. This reaction is used in the synthesis of protein by the plant. Let us have an idea of importance of this enzyme by a typical example. Amount of dinitrogen fixed biologically is estimated to be 175 million tons per year, compared with the total of 110 million tons of ammonia produced by the Haber's Bost process and the distillation of coal. Question: why is a metal as rare as molybdenum so biological important? There are several reasons to address this question. The molybdenate ion has a high aqueous solubility at near neutral pH values, making it easily transportable by biological fluids. The ion has a negative charge, making it more suitable for different environments than are the cations of period 4 transition metals. The element has a wide range of oxidation state, that is +4, +5 and +6, whose redox potential overlap with those of biological system. Being a soft Lewis acid, molybdenum shows a strong bonding preference for the soft Lewis base sulfide. Another important component of these enzymes, nickel. The biochemistry of nickel is poorly understood by all those of period 4 transition element. It is present in some enzyme system in the form of porphyrin type complex. Some of the tropical trees concentrate nickel to such an extent that it makes nearly 15% of their dry mass. It is highly toxic to most plants and moderately toxic to mammals. Cadmium is a toxic element that is present in our foodstuff and is normally ingested at a level that are close to the maximum safe level. Kidney is the organ most susceptible to cadmium. Cadmium ingested 20 200 ppm cause several damage. Cigarette smokers observe insignificant level of cadmium from tobacco smoke. Exposure to cadmium from industry sources is a major concern. Use of nickel cadmium battery is becoming a major waste disposal problem. Many reputed companies now accept return of used nickel cadmium battery so that cadmium nickel can be safely recycled. Mercury is hardaceous because of its relatively high vapor pressure. The mercury vapor is absorbed in the lungs, dissolved in the blood, and is carried to the brain. This causes irreversible damage to the central nervous system. It is slightly soluble in water because of very weak metallic bonding. Inorganic compounds of mercury are less toxic as they have less solubility in water. Arsenic is an element essential to life. However, we need ultra trace elements of this trace amount of this element. Anything more than a tiny amount causes arsenic poisoning. Arsenic is measurable quantities caused that through enzyme inhibition. Known metals. The known metals among the essential elements are hydrogen, carbon, oxygen, nitrogen, phosphorus, sulfur, chlorine, and iodine. Majority of these are needed in trace amounts except carbon, hydrogen, nitrogen, and oxygen, which are abundantly available and constitute most of the chemicals in living system. Phosphorus is an essential element for Phosphorus is an essential element for life. It constitutes an important part of energy-rich molecules known as ATP. It is also an important component of bone as appetite Ca5PO4 whole thrice OH, that is calcium hydroxyphosphate, partial formation of fluoropeptide strengthens the structure of teeth and make it less soluble in the acid formed from fermenting organic material in the teeth. Iodine. Nearly 70% of the iodine present in human body is located at one place, that is thyroid gland. It is used in the synthesis of hormones thyroxine and triiodide thyronine. These hormones, this is the structure of a thyroxine molecule. These hormones are essential for growth, for the regulation of neuromuscular functioning, and for of maintaining of male and female reproductive functions. One common cause of goiter is lack of iron in the diet. A symptom of goiter is a swollen lower part of the neck, enlargement in the attempt of a thyroid gland to maximize absorption of iodine in iodine deficiency circumstances. In order to remove iodine deficiency, potassium iodide is added to the common household salt, such a salt is known as iodized salt. Chloride. The chloride ion has a vital role in the ion balance in our bodies. It does not appear to play an active role, but simply act to balance the positive ions of sodium and potassium. It is major anion found inside or outside the cell. It is essential as an initial electrode for higher mammals and plants. Chloride ion is an essential in digestive juices. Deficiency of chlorine ion is infant lead to impaired growth. Nearly 30 elements are now recognized as essential elements for at least some forms of life. It includes most of the elements through atomic number 35 except for beryllium, aluminium, scandium, titanium, gadolinium, and palladium, along with the noble gases molybdenum and iodine are also essential. It is interesting to note that all elements applicable abundant in the human body, with the exceptions of phosphorus, and also abundant in seawater, suggesting without doubt that our family tree has roots in seas. This is a chemical abundance table of element in human body, earth crust and seas. Next is metallophosphorin. Phosphorins constitute an important class of bioinorganic compounds in which a metal ion is surrounded by 4 nitrogens of phosphorin ring. Phosphorins are macrocyclic tetradentate ligand made up of 4 pyrrole ring linked together through methane bridge, such as shown in 5.1 figure. This tetradentate ligand has a conjugated double bond system with 4 nitrogen donor side. 2 of the 4 nitrogen are tertiary nitrogen, while the remaining 2 nitrogens are secondary nitrogens. The tertiary nitrogen atoms form coordinate bond by donating a pair of electrons at each of the metal ion by a coordinate bond, such as shown by the arrowhead. The other 2 secondary nitrogens lose a proton each and form a covalent bond with a metal ion, as shown. Thus, the porphyrin ring serves a tetradentate di-negative ligand. As a result of di-positive cations like iron, nickel, and magnesium, ions will form a neutral complex with porphyrin, which is processed loss to protons, such as shown in figure 5.1. When the 4 pyrrole ring of porphyrins are substituted by organic group other than hydrogen, it is called the porphyrin. The porphyrin are macro tetrapyrrole system with conjugated double bond. Together with various groups other than hydrogen substituted at the periphery of the ring, substituents attached to the ring are usually organic group with the electron withdrawing and electron releasing characteristic. The complexes formed by the porphyrins with the metal ions, generally di-positive, are called the metalloporphyrins. These are biologically important compounds and play an important role in the animal and plant kingdom. Porphyrin ring system is fairly rigid because of the delocalization of electron in the molecule. Although the skeletal structure is very rigid, insignificant variations have been observed among the metalloporphyrins in the interatomic distance between the pyrrole nitrogen and the metal ion at the center, determining the size of the center of hole. For a knowledge of the covalent bond radii, one can estimate that a bond between a nitrogen atom and an atom of the first transition series should be about 2.0 angstrom long. In brief, an ideal size of the atom to be fit in the hole is 2.0 angstrom. Thus, size of the hole in the center of porphyrin ring is ideal for accommodating metal ion of first transition series or lighter alkaline earth metals. A metal ion of appropriate size sitting at the center of porphyrin ring will be surrounded by 4 nitrogens of the pyrroles and forming a square planar geometry. It means that the metal ion and the 4 nitrogen lie in the same plane as shown in the figure 5.1. However, when the size of metal ion is smaller than ideal, the ring will be reluctant to accommodate precisely the metal ion. In this way, the ring will either readjust and distort itself in order to accommodate the metal ion. On the other hand, if the size of metal ion is larger than ideal and the transition metal ion cannot be fit in the hole and stays out of the plane of the 4 nitrogen atoms, it means that metal atom site above the plane of 4 nitrogen atoms and acquire a square pyramidal geometry. The nature of metallopyrines vary with the nature of metal ion and the type of inorganic group attached at the 8 positions of 4 pyrroles ring around the periphery of pyrrole. A group of related compounds, the phthalocyanines, shown in figure 5.2 of isoelectronic with the pyrines. These compounds are interesting because of their intensely colored metal complexes, which are to be almost commercial application in dyes and pigment. The size of the hole in these phthalocyanines ring is about 0.1 angstrom smaller than in pyrroles as a result of nitrogen amount compared with carbon. Compared, the covalent radii of carbon is 0.77 angstrom and nitrogen is 0.75 angstrom. This is molecular structure of metathalocyanines complexes. Two of the most important metal complexes of pyrines are chlorophyll and heme, which are being discussed. Chlorophyll is a magnesium complex of pyrines which play an important role in photosynthesis. Photosynthesis is the Mercalli redox reaction in nature that converts water and carbon dioxide into sugar and oxygen in the presence of sunlight. This is the reaction. Carbon dioxide and water will give glucose and oxygen. This process is the primary source of food that we eat and molecular oxygen that we breathe. The function of chlorophyll molecule is to absorb photons in the red part of visible spectrum and pass this energy to excitation to other species in this reaction chain. The ability to absorb the light is due to conjugated polyene structure of porphyrin ring system. The role of magnesium is to make the entire molecule rigid so that energy absorbed is not easily lost. There are a number of similar and non-identical chlorophyll molecules. It is important to note that chlorophyll A is the basic porphyrin system that has been modified in two ways. The pyrrole ring for one of the double bond has been transhydrogenated to form a magnesium dihydride porphyrin complex. In addition, a cyclopentone ring has been fused to the side of pyrrole ring third in figure 5.3. This is the structure of chlorophyll A. In brief, adsorption of sunlight by chlorophyll is the first step of conversion of sunlight into unstable energy by plants. it will not be out of place to stay. Chlorophyll are nature's solar energy collectors. Heme is an iron foreign which is present in hemoglobin, and myoglobin which is being discussed. Hemoglobin and myoglobin. Molecular oxygen plays an important role in biological system because of its importance in respiration. Formation of oxygen, we have already learned, in nature involves a number of reactions such as redox reaction, electron transfer, atom transfer, and photochemical reaction. A number of protons are known that bind and transfer oxygen to different extents. Such proteins that bind oxygen are called oxygen carriers. The most important and well documented protein that bind and transfer oxygen are hemoglobin and myoglobin. Hemoglobin and myoglobin are very closely related to each other. Hemoglobin is a large protein with molecular mass 64500 and consists of 4 subunits. Each subunit is made up of a heme group associated with a protein called globin. It is important to recall that each heme group is composed of iron surrounded by 4 nitrogen of iron ring ligands. Hemoglobin is a large intracellular protein that is responsible for red color of the blood. On the other hand, myoglobin is a relatively small protein with a molecular mass of 17,000 and consists of only one heme group and a polypeptide chain. It is important to recall that peptide chain consists of 150 and 160 amino acids residues flooded by the single heme group. Myoglobin is a small intracellular protein in invertebrate molecules. Myoglobin was the first protein whose X-ray structure was stabilized in 1959. In 1962, the Nobel Prize in Chemistry was awarded by Kindrew and Pradeep for the work of structure of a globular protein including myoglobin. The basic functions of hemoglobin and globin are following. Hemoglobin picks up oxygen in the lungs and transport to the rest of the body. Myoglobin accepts oxygen from the hemoglobin in the muscle and stored it until need for energetic processes. Deoxygenated hemoglobin used some of its amino acids to fix carbon dioxide and then transport carbon dioxide back to the lungs. Oxygen carriers perform the function of acquiring oxygen from the atmosphere, transporting it through the circulatory system for the organisms, and delivery it to location where it is used. They all bound O2 rapidly and reversibly according to the equation 5.1. Protein plus oxygen will give protein oxygen. The equilibrium must be largely to right at the oxygen concentrated available at the pickup location. For example, lung air interface, muscle cell body interface, and mother fetus interface at the placenta. It is important to note that the oxygen carrier interacts strongly with oxygen to bind it. However, it carries must to undergo irreversible oxidation in the process. In brief, hemoglobin pick up oxygen in the lungs and transport it to the site of use inside the muscle cell. This oxygen is transferred to the myoglobin, which stored it until required for metabolic actions, in which O2 is reduced to CO2. Deoxygenated hemoglobin then transport O2 back to the lung. Structure of hemoglobin and myoglobin. We have already mentioned that the structure of hemoglobin and myoglobin are very closely related to each other. Hemoglobin is a large protein and consists of 4 subunits. Each subunit contains a one heme group associated with proton globin, such as shown in figure 5.4. This is structure of first structure is heme and the second B structure is hemoglobin. The iron is held in position of coordinate with the nitrogens of heme and imidolase of globin complex. This complex reversibly with oxygen as shown in the figure 4.5.4b. Thus, hemoglobin is the oxygen carrier of blood and the red color of blood is due to the oxygenated hemoglobin. It is important to note that the 4 sites units are similar but not identical. 2 subunits from alpha and alpha chain of 1 for 1 amino acid, while other 2 subunits from beta chain of 146 amino acid. These chains are coiled together to give a 3-dimensional network. A systematic structure of hemoglobin showing the relationship among the 4 subunits of tetramer shown in the figure 5.5. Structure of myoglobin. Myoglobin is a small protein compared to hemoglobin. It consists of a single heme group embedded in the polypeptide chain called globin. The peptide chain consists of 150 to 160 amino acids folded about the single heme group as shown in the figure 5.6. The heterocyclic ring system of the heme consists of pyrrole containing pyrrole groups labeled as A, B, C, D linked by the methane bridges. The iron atom in the oxidation 2 present at the center of heme is bonded by 4 nitrogens of pyrroles system together with 1 nitrogen atom is imidolose side chain of histidine residues, which is a part of the long peptide chain of amino acid residues. It is this polypeptide chain that plays an important role in the biological fixation of molecular dioxygens. A simple outline of the structure of myoglobin showing heme group embedded in the polypeptide chain is shown in figure 5.6. It is important to note that the hemoglobin and myoglobin have 5 coordinate iron atoms. The oxidation state of iron in hemoglobin and myoglobin is +2. The iron atom is bonded to 4 nitrogen atoms for pyrrole ring and 5th nitrogen from the protein chain. In both the compound, the 6th position is occupied is weakly bonded to water. Hemoglobin and myoglobin in such complexes are named as deoxyhemoglobin and deoxymyoglobin respectively. However, when molecular oxygen occupied with the 6th position, which is trans to histidine chain, then the molecules are named oxyhemoglobin and oxymyoglobin respectively. A myoglobin polypeptide is comprised to 8 separate right-hand alpha helices designed from A to H that are connected by known helical regions. Role of hemoglobin and myoglobin. Hemoglobin and myoglobin play critical role in transporting dioxygen from lungs to tissue and carbon dioxide from tissue to the lungs. The function of hemoglobin is to bind oxygen at high oxygen partial pressure found in lung tissue to form hemoglobin dioxide. Hemoglobin carries this oxygen without loss through the blood and then release it to the myoglobin. In other words, the dissociated oxygen from hemoglobin diffuses to the tissue when myoglobin picks it up and stores until it is needed. It means that myoglobin has greater oxygen efficiency than hemoglobin at lower pressure. Hemoglobin and carbon dioxide are then returned to the lungs where carbon dioxide is exhaled. It is clear from the scheme 5.2 that follows hemoglobin and myoglobin play cyclic role in transporting oxygen from the lungs to the tissue, and carbon dioxide from the tissue to the lungs. The carbon dioxide is carried out in the form of HCO3 negative ion. Carefully analysis of the scheme suggests that the partial pressure of O2 is high in the lungs, about 100 torr. This is responsible for formation of HbO2. However, the low partial pressure of oxygen in the tissue, 20 to 30 torr, is responsible for dissociation of HbO2. The dissociated oxygen O2 diffuses into the tissue and oxides the metabolic fuels to copper, carbon dioxide and water. The carbon dioxide evolved is exhaled in the lungs. Oxidation and oxygenation of hemoglobin and myoglobin. The heme group consists of iron ion embedded in a pyrene ligand. The iron ion has 6 coordination sites. The porphyrine link takes place of 4 to 6 sites, leaving two free binding sites on opposite side of metal line. If a free heme is present in aqueous solution, 2 vacant sites may be occupied by water molecule. In an aqueous solution containing oxygen, a free or naked heme group binds to oxygen molecule in an irreversible manner with the oxidation of iron 2 positive and iron 3 positive ion. This oxidation of iron Fe2 positive and Fe3 positive destroys the oxygen binding activity of iron. This unproductive oxygen in a biological system is potentially fatal. The irreversible oxidation of free heme in the presence of oxygen involves a series of dimerization containing of 2 Fe ions, Fe3 positive ions that is shown in figure 5.7. Next is nitrogen fixation. There is a large amount of nitrogen gas in the atmosphere, that is 78%. However, plants are not able to utilize this nitrogen because of its relatively unreactive nature. The unreactive nature of dinitrogen is described to its very high bond strength, that is 945 kilojoule per mole, due to the presence of triple bond between two nitrogen atoms. Soil that are very fertile contain nitrogen in the form of nitrates, nitrites, ammonium salt and urea. All these compounds are absorbed from soil water. So soil water through the roots of the plant. The continuous uptake of nitrogen by plant reduces the fertility of soil. In order to fix nitrogen, that is to make nitrogen reactive towards other substances to produce nitrogen compound, it is necessary to use energy richer conditions. This process of conversion of atmospheric nitrogen into useful compounds such as ammonia is called nitrogen fixation. In 1965, Kaiser Sanoff, a Canadian research student at the University of Toronto, was studying the reactions of ruthenium chloride with the hydrogen hydrated. He synthesized a brown compound by combining ruthenium chloride with the hydrogen hydrated, but was unable to explain the chemical composition of the compound. From one fine day, during the discussion with another chemist, he got an idea that this brown compound may contain dinitrogen bond to the ruthenium metal, similar to the bonding of carbon monoxide with the transition metals. He reported this excited news to his superior, Bern Allen. After several months, Sinoff and Allen submitted the manuscript of their research finding to a journal for publication. The manuscript was rejected because dinitrogen is known to be as inert as noble gases. However, Sinoff and Allen again appealed to the editor of the journal. The editor sent the revised manuscript to 16 other 16 other celebrated inorganic chemists for the comment, and they are agreed with this discovery, and research paper was published. As a result, the world of inorganic chemistry was changed, suggesting that dinitrogen is not longer unreactive, and first compound of dinitrogen was born. The first dinitrogen compound of can be readily prepared from aqueous ruthenium chloride using hydrogen hydrated in aqueous solution. The pentaamine ruthenium cation was formed and could be isolated in a variety of salts. Today, almost all the transition elements are known to give dinitrogen complex, and more than 200 such compounds are well characterized. Several new methods have now found that for the preparation of complex containing pentaamine ruthenium cation, a direct method involving nitrogen gas involved prior reduction of pentaamine ruthenium salt with zinc as given in reaction. The stronger nucleophilic nature of dinitrogen group is shown in the above reaction, where coordinated water is easily displaced by gaseous dinitrogen. Another interesting example of strong nucleophilic nature of dinitrogen is shown by the formation of a bridged complex. Another general method for preparing of metal complex of dinitrogen involves the reduction of metal complex, especially of MO and W, in the presence of suitable coenzyme under nitrogen gas. These are some reactions. Nitrogen can coordinate to the metal in four ways shown below. However, E and D1 on mode, as well known as exemplified in structure 1 and 2, the formation of stable dinitrogen complexes lead to study with Other transition metals complexes with titanium are most promising. It has been found that titanium alkoxide can easily reduced with the subsequent release of ammonia and hydrogen. A complete cycle of a reaction depicting the fixation of atmospheric nitrogen to ammonia and X-ray study of complex indicated that RuNN linkage is linear in a relatively compound where co-link triphenyl phosphazine. The molecular structure is shown in the figure 5. The CONN linkage is almost linear with an angle of 178 degrees. The bonding in a nitrogen gas complex resembles that of a carbon monoxide complex. Back bonding of electron density from the metal of pi anti-bonding orbital is clearly reflected in the shortening of CONN bond, that is 1.807 angstrom, which is closer to the cobalt and carbon monoxide bond than this in cobalt and NH3 bond. In amine complexes, the NN bond length is longer than found in the molecular nitrogen, suggesting a weakening of nitrogen-nitrogen triple bond from the electron density in anti-bonding orbitals of nitrogen. Compare the value of 1.116 angstrom for bond order from 2.54 and positive. Over several hundred compounds of molecular nitrogen with transition metals are known today. This new discovery of stable metal dinitrogen complex led to extensive investigations of the possible of fixation of nitrogen. In other words, major interest lies in converting metal nitrogen complex with appropriate reducing agent to convert N2 into ammonia under ambient condition. Dinitrogen transition metal complexes of MO and W have been shown to protonate the coordination dinitrogen and diazine, isodiazine, hydrido and hydrazine. For example, where M is MO and WX is halide and DP is diphenyl phosphoethane. In this reaction, the reduced product N2S2 has been assigned with diazine structure H and double bond NH. It acts as two electron donor. All attempts to reduce N2S2 further to N2H4 and NH3 by using stronger reducing agent have not met with success. On the other hand, dinitrogen metal complexes with monodentate co-ligand have successfully been reduced to give ammonia. For example, the complex cis associated with monodentate co-ligand dimethyl phenyl phosphogene on treatment with sulfuric acid in the presence of NaOH followed by distillation offered high yield of ammonia with a trace of hydrazine.